change the background. Okay, good morning. Today we will continue with our next module, longitudinal dynamics, which we have started in the last class. Looking at longitudinal dynamics of a vehicle refers to vehicle performance study. That means what is the vehicle capability to accelerate or to brake or decelerate or to negotiate a slope is what is referring to vehicle performance study, and it is in straight line motion. So it is in straight line motion, so we call that as an 1D motion. So in the last class we were essentially started looking at what are the various forces that are acting on a vehicle as the vehicle accelerate along a gentle slope, and then we were able to derive the expression for what is the normal reactions or the normal loads that are acting at the wheels of the vehicle, axle of the vehicle. So that's what essentially we did in the last class, and we were able to look at those expression of WF and WR. They have got essentially two parts. One is static load distribution part, another one is dynamic load distribution part. So I'm going to start from that point and to complete the derivation of deriving the maximum tractive effort, and then we will continue with the power plant and transmission characteristics, right? So let me share my screen for today's class. So hope you are able to see the screen, and in this is the last class lecture slide, and we essentially looked at an important term called longitudinal slip. So longitudinal slip is essential for the generation of tractive effort at the tire rod interaction, right? So we will study this detail again on a tire and particularly various tire models. At that time we will again revisit this and look at it, right? So you can analogous way compare this with your lateral force, where you are able to express that as a product of cornering stiffness and slip angle. The similar way you can now express the longitudinal force or the tractive effort at the tire rod interaction generated is the product of longitudinal slip stiffness times the longitudinal slip. So this I is what is defined as here, and we will revisit them once again later on. And with this understanding of variation of effects as function of longitudinal slip, we were just looking at the free body diagram of a passenger car and all the external forces that are acting on the vehicle as that is accelerating up the slope. And since it is accelerating up the slope, there is essentially here D'Alembert's force. That's what is an inertia force that has to be introduced for the dynamic equilibrium of the vehicle. And then we were able to derive these expressions, and we were able to write the forces at the tire rod interaction as tractive force, total tractive force minus rolling resistance, is what is essentially all the other resistances that are in your vehicle. And this is an important equation. We again looked at these two moment balance equation about point B and A to get your normal reaction in the front axle and the normal load at the rear axle. And we express that in terms of tire forces acting in the tire wheel and road interaction by equation 8 and 9. So we are just going to start with this two equation and today's class and continue our lecture, right? So this is lecture number 37 and today's date 24/11/2021. And we are going to derive the maximum tractive effort. For that, let us look at again this WF. What we derived is WL2 by L minus F minus RR by L. Here it is into H. And WR is WL1 by L plus F minus RR minus rolling resistance by L into H. So this first term is what is referring to static load distribution. The second term is what is referring to dynamic load transfer. So during your acceleration of your vehicle, you have your normal loads given by these expressions. Right. So now to get your maximum tractive effort in terms of vehicle parameters, I'm just going to replace your rolling resistance force by this expression Fr into W, because the rolling resistance again depends upon many factors. One important factor is normal load, and this is what is called the rolling resistance coefficient. So let us look at this rolling resistance all again when you look at the tire in detail. At the moment, please take granted this equation. And let us look at now here, this F is to be on this side. We require this has to be the expression of F is what we needed, right? And we have looked at this will be limited by the maximum traction that can be developed would be limited by what MEE times W is what is the condition. So if that is so, if I have my all wheels are drive wheels of a vehicle, if I consider, that means I will have Fxf as well as Fxr. So that would be limited by MEP times Wf and Wr. So if it is Fx max of the front axle, then it is MEP times Wf, and Fx max at the rear axle, then it is MEP times WR. So you can have a vehicle, front wheel driven vehicle or rear wheel drive vehicle. In such cases, your expression of maximum tractive effort would be this. So now looking at this equation 8, and we had this is 7 and 8 or 8 and 9. So we had derived this as 8 and 9 equation. So this is 8 and this equation is 9. Now, considering your vehicle is a rear wheel drive vehicle, for rear wheel drive vehicle, I would have my maximum tractive effort that will be given by MEP times WR. So Fx max would be mu P times WR. So that's going to be mu P times this WR I have to substitute. So that's going to be WL1 by L plus F. So this F is what is the tractive force. That is also here F max that comes here along with that. So this minus RR by L into H. Right. So this RR now can be replaced by FR times W. So I have here the W term, here also the W term, and there is an Fx term here. So I have to group this on this side. So I require maximum tractive effort. So I have to bring this term on the other side. So it is going to be F max, Fx max minus Fx max H by L. H by L, because the H is common factor here and that comes on this side. And on the other side, I would have now that is mu P times W. If I take it out, this is going to be L1 by L minus FRH by L. FRH by L. So now my Fx max. So here, looking at this side, this. If I take f x max outside, I'll have 1 minus, sorry, this here you also have this mu ph, so there will be mu p here. So it is going to be mu p w into L1 by L minus FRH by L divided by 1 minus mu p h by L. So this is that expression, expression 10 for the maximum tractive effort that can be developed in a rear wheel drive vehicle, right? In a rear wheel drive vehicle. And similarly, if it happens to be front wheel drive vehicle, you can derive the expression simply like this: for front wheel driven vehicle, so you will have F max is given by mu p times wf. So I will have to substitute same way mu p times this w L2 by L minus F max minus FR W by, so here is the minus sign, here it was plus sign, right? That's only difference. This into H by L. So rearranging the term similar to that for rear wheel drive we did, you will have now F max for front wheel driven vehicle, that's going to be mu p times W into L2 by L plus, so this is here going to be minus, the terms come here, so it will change, right? Plus or minus, yeah, in this case it is plus F R H by L divided by 1 plus mu p h by L. So this is equation number 11. So this is the expression of maximum tractive effort that can be developed in the front axle for front wheel driven vehicle. So this entire derivation, we had some important assumption. What are those assumptions? We have not looked at the rotational effect that can be coming from your engine. So engine can be of longitudinally mounted engine or transversely mounted engine with reference to its crank shaft axis. So if it is longitudinally mounted engine, then you would have a load transfer as lateral load transfer, and that is neglected. If it is transversely mounted engine, because of an engine rotation, and there will be a longitudinal load transfer, such kind of local load transfer coming from the engine is neglected. That's an important assumption. We do not look at the rotating elements and their impact on to this tractive force, that is expression that we have derived, right? So with that, keeping that in mind, you can just use these equation whenever you have to estimate your maximum tractive effort and we are given a vehicle parameters, right? So in this expression, you can see the load only is there. Rest of this is the road coefficient, road elevation coefficient, rolling resistance coefficient, and this rest of all things are the geometry of your vehicle, right? Yeah. So here it's where we have to again restate the statement that we did in the last class, that always this performance potential of your vehicle for its performance is limited by two values or two limiting factors. The smaller of that is deciding. That's what we said. What are the two limiting factors? So one is this maximum tractive effort that the tire ground can develop. So we derived an expression for maximum tractive effort, F max, that a tire road interaction can support. So this is what it can support. The second factor is that comes from the tractive effort that the engine torque with a given transmission can provide. So engine torque. So Fmax due to engine torque with the appropriate transmission that can provide. So the can support and can provide is the two keywords here to be looked at, and the smaller of that would always decide your performance potential. So when I say that's a performance potential, that is essentially for to accelerate your vehicle or to decelerate or brake the vehicle or to negotiate the grade of your road surface. So this is what you have to look at it. So what can be deciding? That's what is the question now, right? So when the smaller of these two would decide the performance potential. So when is that always the tire rod interaction is going to be smaller than an engine torque or vice versa? That is not so. So that's what we have to now physically you have to look at what's happening with your vehicle when you drive, right? So for example, you see at low gears, what does that you mean? The first gear when I put my vehicle and drive, when I do that, whenever I require to negotiate a grade or fully open throttle. See, the first gear I have to get the maximum tractive effort to negotiate a grade. At that time, what is going to decide my performance potential? It depends upon most of the time the first factor, tire rod interaction. What I mean by that, I can have my vehicle with the full throttle open and it can provide a maximum tractive effort at the first gear. But to have my gradability, it is going to be dictated by the surface characteristics of my vehicle. So if my road surface is slippery surface, even though the engine provides a maximum tractive effort, but what is going to decide your gradability of your vehicle is the what is that maximum tractive force that can be supported by the road surface. So that's where you see at the lower gears generally what would be the deciding factor would be your tire rod interaction and the MEE value of the surface decide that. On the other hand, if you look at high gears means what? Upper gears, I straight away have my direct drive equivalents. So in such cases, my vehicle speed would be higher, and higher speeds, if you look at what is going to decide is the engine torque output is going to be smaller than that of what that can be provided by MEP times W. So if I take a given surface, this is a debatable part. If I take a good rough surface road, it is not slippery. Generally, the MEP times W will be the limiting factor at the low gears of your vehicle. Whereas, on the other hand, in a higher gear, high speeds of your vehicle, you see that the limiting factor is the torque that is provided by the engine. So that would be a smaller value than that of what MEP times W can be supported by the road. So at that time, it is decided by engine torque output. So this is what something to be kept in mind. If that is so, I cannot neglect, because you are not going to drive your passenger car, not always at a first gear. So we drive in highways in higher gears. So at that time, the limiting factor happens to be your engine, power plant, and transmission characteristics. So we have to understand them so carefully. So for that purpose, I'm just going to take now an engine power plant, particularly in IC engines and their performance characteristics, and hence the requirement of transmission system in order to get your maximum tractive effort is what I'm going to teach you in today's class. And in this scenario, we have when I say power plant of a passenger car, it is not necessarily only ICE engine based power plant. In near future, we are going to have electric vehicle driven cars, or the electric driven vehicle cars are given by battery source, the energy, or by fuel cells. There are many research that are going on. So in such cases, also the requirement of your vehicle translation is depending upon essentially this type of power torque characteristics, right? So what is that this type of power torque characteristics I say? So if I take vehicle speed on horizontal axis and I have my tractive effort for tractive effort, or I could call that as, instead of tractive effort, called torque variation, because that is more apt. So what is the power requirement when I speak? I would say in terms of torque requirement and power requirement. So power requirement of your vehicle is always to be a constant power requirement. That's what is an ideal requirement. Ideal requirement. And this is what power. So power needs to be constant irrespective of the speed of my vehicle. This is what is an ideal requirement. And that would be fulfilled by my variation of torque. So the torque variation is going to be hyperbolically varying like this. Like this. So it means what? At the smaller speeds, when I have to have my vehicular application, the power plant of my vehicular application should provide at low speed higher torque and high speeds lower torque, so that the power would be torque times omega will be constant always, right? So this is that the ideal requirement of any vehicular application that has to be provided by your power system in your vehicle. So now you see here at a lower, the same earlier point, at low speeds, the higher torque when it has been given, the engine can provide this high torque, but what is going to limit your performance is the tire rod interaction condition. At a higher speed, the engine would provide your lower torque, but at high speed, your MEP times W, though you get it, and that would be having higher value, maximum traction that comes from the tire rod interaction value may be more than that of an engine at that time. So your limiting factor at high speeds, higher gear would be the second point, and the first point would be for the lower gear. So this is how you can also always remember this too, and which is smaller is going to decide your performance potential. So you see there are application of vehicle. One is the passenger car, other vehicle, if you look at heavy vehicles, which can be in an industrial application, or the vehicles which are in agricultural field, and they require to have more torque rather than the speed of your vehicle, right? In such cases, at low speeds operating, you will see that the vehicle would have a prime mover ICE engine based, diesel engine based vehicle. Whereas a passenger car, you have though the diesel based version as well as your gasoline based IC engines are there, and they have to be meeting this requirement. So now the question is that power torque characteristics of your IC engine is similar to that? If that is the question, if I ask you, you should answer that that is not so. The power torque characteristic of an engine, if you look at, and that is not the same what is this required ideal power for the vehicular application. Then how those are applied on your vehicle is the question there. Next question. Then how are they employed on those vehicles? Many decades that we have been witnessing, they are employed in your vehicle. That's all because of the advantage of having high power to weight ratio, good fuel economy, and relatively lower weight and ease of operation and so on are the deciding factor, and that has been researched and made them to map for this requirement, right? By means of an appropriate transmission system. That's where transmission system is there. If we do not have an appropriate transmission system to account these two requirements that we are talking, and intermediate speed requirement, and we will not be able to have an output power constant felt for the engine vehicle application, or the torque supplied by your engine has to be meeting higher torque requirement at the low speed of a vehicle, especially to grade the vehicle. On the other hand, you require more speed with the lesser torque requirement. So now to understand what is the characteristic of the engine is important, right? Let me just draw the power characteristic of the engine, and that we will look at it. So here I'm just going to take the output power in kilowatts. This is power of the engine. I'm going to draw that as function of speed. So the speed of engine, not vehicle, speed of the engine. So the speed of the engine is generally given in RPM. So let me take the petrol engine or gasoline engine is up to say 6000 RPM, just to take it. So this is 2000, 1000, 2000, 3000, 4000, 5000 and 6000 RPM. And I also have another scale here, which is for torque, engine torque. Right, so if I have this, my variation of power would be, so the engine would start running smoothly at a particular speed when it is attained, and that speed is what is called an idling speed of the engine, So then it will have its smooth operation of the engine to provide the power output. So you would have your graph starting from some idling speed, say this 1000 RPM, and then the power keeps increasing, and that would attain some maximum power, and then it will rapidly fall. So this is what is power characteristics. This is what is the power characteristics, right? So good combustion quality would be achieved in the intermediate speed. So when I say that good combustion quality, I would have another scale to represent my specific fuel consumption, and that would be somewhat changing like that. At lower speeds it will be like this, and the scale would be now between 0.2 to 0.2 to 0.25. Right, this is called the specific fuel consumption. Fuel consumption. Specific fuel consumption. And the torque variation, I will have the scale here. So the torque may be 160 Newton meter till 200 Newton meters. So these values for a typical vehicle engine that I look at. And the torque, if you look at the variation, is not like a hyperbolic variation that you have seen in the earlier plot. So that would be varying something like this. So it will be increasing and it will be falling so sharply like this. So this is the torque variation. So you see that you have a maximum torque at the mid frequency range. At the mid speed, intermediate speed, you get a maximum torque. It is not so at the lower speed, and beyond that speed, you see there's an rapid drop in torque. That too, especially after your maximum power time, right? So this is how your power, torque, and fuel consumption characteristics of your gasoline engine, petrol engine. So this engine now. Um, to be used in a power plant of your vehicle, correct? So what does that requirement? I require the speed of my vehicle with the torque requirement is this, right? So this would be achieved with an intermediate speed. So I will have these speeds and my engine can be provided with an appropriate transmission system so that that characteristics can be exploited like that. So I would have my engine power output or the torque obtained for that range of speed, and I will have that characteristic comes here. So next range of speed, the characteristic of this is like that. So when I have my engine characteristics in an intermediate ranges like that, so this is at the lowest gear. If I provide an appropriate transmission to take care of the output of my engine and to take that motion to the drive axle, and I would have in my first gear, this is in first gear, this is higher gear or the last gear. The last gear, you will have this, and if you map this, if you are fitting a curve here, you see this torque requirement is fulfilled as per the requirement, ideal requirement. That is how transmission can play a role in bringing in your IC engine application viable for your vehicular application. So any doubt at this point? Do you have any doubt at this point to understand this? If you do not have doubt, let us proceed further to look at the transmission characteristics. So similarly, one can look at diesel engine characteristics. Only difference there you would see is this operating speed is not going to be higher, that would be smaller as the requirement of diesel engine, mainly for the heavy vehicles application. If you look at, they would be operating with a smaller speeds requirement because they are essentially required to provide higher torques at low speeds, right? So now let's look at the transmission characteristics. So when I look at transmission characteristics, so you can have many types of transmission. So we always like to have manual gear transmission system. So in our vehicle, we have manual gear transmission system. And you see nowadays that the transmission system also has got its advancement. We have an automatic transmission system with an application of torque converter, and we have continuously variable transmission system. We also have hydrostatic transmission system in heavy vehicles and so on. So there are many classification of your transmission system, but essentially all the transmission system is to provide you an ideal torque speed or ideal power speed characteristics, right? So that is to be kept in mind. And let's look at now how this transmission system is designed for your passenger car, right? Or for a heavy vehicle. So if you look at this transmission system comes with a set of assembled components or assembled subsystems. It essentially will have a clutch, and it will have a gearbox, a propeller shaft, and a differential. And your drive axle. So these are all essentially constitute your transmission system, typically for your rear drive vehicles, right? You also have vehicles with the transaxle. So what do you mean by transaxle? Transaxle will be one which would be generally witnessed in front wheel driven front engine vehicle or rear wheel drive rear engine vehicle. So engine and your transmission should be an integrated part. So these all things. You'll not have a propeller shaft. You'll have your gear, clutch, gearbox, differential, drive axle. All would be an integrated unit called transaxle, right? Transaxle. So you see that we also have direct drive propulsion system. What do you mean by direct drive propulsion system? You cannot have an engine directly coupled to your wheels. Direct drive, that's not possible. That's where your transmission system there. But you can tap the engine speed as it is, whatever that you get it from its output on your drive wheels, and that is what is direct transmission or no reduction drive, and no reduction drive, and that's what is achieved by your appropriate gearbox design, right? Appropriate gearbox transmission design, right? And that would be achieved at the highest gear of your gearbox. So when I say transmission system, it is called N speed transmission, N speed transmission. So it would be 3 to 5 for cars, or it can be from 3 to some 16 for heavy vehicles. So you can have your gearbox or the speeds that is felt at the drive axle may be varied from 3 to 5 in a passenger car, or 3 to 16 in your sorry, it's from 5 higher, minimum 5 required for a heavy vehicle, 5 to 16 in a heavy vehicle transmission. You also have to understand something called overdrive. Overdrive. Yeah, right. Overdrive axle. So what do you mean by overdrive axle is that our overdrive gear, it's not axle, overdrive gear. We call that as overdrive gear. Overdrive gear, right? So overdrive gear refer to that the output speed of your drive axle will be more than that of the output that comes from your engine, right? So that will be maybe 15% more or 30% more. So this there will be a drive overdrive gear employed at the drive wheels itself, and that would create the speed output more than that of the speed that can be given by your engine output. And you know what is the main function of a clutch? Clutch has to get engaged with an engine. Then only the power from the engine can be transmitted through the transmission system. You will disengage the clutch, and then that would ensure that the engine will not stall, and then it would be rotating. It won't be stopped when you have to wait in a signal. So you see that you put your vehicle in neutral gear. So and or when you have to drive and you have to go smoothly, then you are pressing the clutch. That means you are disengaging your transmission system from the engine output. So the engine output and the transmission gearbox input is connected by this clutch, right? And the gearbox, this n speeds, how are they achieved? That generally follows something called a geometric progression for an intermediate gear speeds, But for the lowest gear and for the highest gear, the requirement is decided based on the requirement of your vehicle. So the gearbox design, if you look at, you have your first gear, that is first gear, or you call the lowest gear, or you say higher reduction gear, higher reduction gear. That means what? Why it's called higher reduction gear? The speed of the engine would be say more, but the speed at the drive axle would be very less. So that's the smallest. So the vehicle would have the speed, very small speed. Even engine is given with the higher speed, with its full throttle during your grading of the hill. But the speed felt at the vehicle would be the smallest gear. So that's what will be the first gear function. So the first gear design is accounted by looking at the gradability of your vehicle. The vehicle, car has to grade 30% of the slope, 30% slope it is called, or 0.33. That how do you get that? What is the deciding factor? So that's what is for the first gear. So what is that deciding factor? So let's look at this equation for that. So what is that equation? I'm just going to write now. You'll understand. Is this. So just now we derived an expression for maximum tractive effort that can be developed at the rear wheel drive or front wheel drive vehicle, right? So if you look at that, let me write now an expression of rear wheel drive F max, for rear wheel drive F max is what mu p times W into L1 minus FRH. This is all by L divided by 1 minus mu pH by L. So this is the expression just now we derived at the beginning of the class. That is that can be supported by the road surface, right? When it is of rear wheel drive vehicle. So here we looked at in this parenthesis, that is F minus RR, and that would be equal to RA plus RG plus D and so on. So RD is draw bar pull, RA is aerodynamic resistance, RG is your grade resistance and so on. So in this case, as I consider my vehicle, the smallest gear, generally we take the vehicle in a slope with the smallest gear to provide a maximum tractive effort, and the speed of the vehicle is very small, and I can neglect this aerodynamic resistance there. And I can also consider I drive up and I don't now look at for a passenger car what is my drawbar pull. So that only is the grade resistance. So this grade resistance is what we know that as W sine theta S is what is the grade resistance. So if I take that now as a basis, what I can do now, this maximum tractive effort would be now W sine theta S max, maximum grade angle, because sine theta is approximately equal to tan theta at the smaller angles, right? This can be your grade. So this plus your RR, this plus your RR, right? So if that is so, I wanted what now this. So that expression would be W sine theta S max would be provided by mu P times W into 1 minus FRH by L. FRH by here also is there by 1 minus mu P H by L minus RR minus FR times W. So you have to look at this way. So if I consider this is my basis, for uh, for deciding my the requirement of speed. I will define now this term. What is this? Zeta 1. So what is the zeta 1 is referring to is lowest gear. This is lowest gear ratio. Lowest gear ratio. So this zeta symbol here is a gear ratio. Subscript 1 is the first gear. So that would have to provide now this. So what is that maximum tractive effort provided at the drive axle divided by that comes from the engine. That comes from the engine is what is this lowest gear. So that would be ME max, maximum engine torque, and there would be an efficiency. There would be an efficiency of transmission efficiency, and also there is another reduction called axle, drive axle gear ratio, gear ratio, correct? So that's what is called the drive axle reduction ratio. So this is what is that requirement for the first gear. So if this is that for the first gear, I have to substitute these two terms. So I will have this mu PW into L1 by L minus FR H by L by 1 minus mu PW mu PH by L minus FRW, right? So that's going to be a numerator divided by, I will have this ME max T into axle, right? So this is what is going to decide my lowest gear. So I'll stop at this point and then we will again continue in the next class. How do you go about deciding your gearbox intermediate for intermediate speed reduction ratio and the highest gear reduction ratio. In the next class, we'll start looking at it on this Friday's lecture. Right. So I'll stop at this point. If you have any doubts, you can ask. Otherwise, we will discuss again in the next class.